The last normal form that we're going to look at is the one that is called the Reed-Muller Canonical Form, or shortened as RMF. So there is a theorem that says that all Boolean functions can be written with the ring operations, that is addition and multiplication, by using the Reed-Muller Canonical Form. And this is written as the Boolean function f of x is a sum of multiplications, or a sum of AND operations, or AND terms. And AJ here belongs to the set B, which in our case is 0 and 1, and IN of j is just an index function that will point to which indexes are we going to use in our AND terms. And addition and multiplication in our case are here given as modulo 2 addition and modulo 2 multiplication. This normal form has other names as well. A very common name to use is the Algebraic Normal Form, which is shortened as the ANF. Another name for this is the ring sum expansion, which is shortened as RSE. So all of these just refer to the exact same representation of the Boolean function. They are just used in different domains and in different areas. So if we have a Boolean expression, how do we derive the Reed-Muller canonical form? One alternative is to use the definition of the Boolean operations. So we can immediately use the fact that A and B can be written as A times B, and A or B can be written as A plus B plus AB. And then we have that A prime, or not A, equals 1 plus A. Another way to derive the RMF is to use De Morgan's law to get rid of all our OR terms, and then we can also use the fact that A prime equals 1 plus A. A third alternative is to first write the function in the disjunctive normal form, and then we use the fact that mi or mj, where mi and mj are min terms, can be written as mi plus mj plus mi times mj. But since mi and mj are min terms, it means that they contain all the different variables, and if they are different min terms, there will be at least one variable that is xi, for example, in one of them, and xi prime in the other one. So these will always cancel out. So this can always then be written as mi plus mj. And then here in this method of writing the function in RMF, we are also going to take advantage of the fact that A prime can be written as 1 plus A. So using these two expressions, we can get the RMF from the DNF. Then the final way of deriving the RMF is to use something that is called the Reed-Muller transform. But this is not something that we're going to look at further here. So let us look at an example of how we can derive the RMF from a Boolean function. So we have this Boolean function that we call g of x, which equals x1, x3 prime, or x1, x2. And now we can use the definition of our Boolean algebra in order to write this as x1, 1 plus x3, and I will just use ordinary plus here for simplicity, plus x1, x2, plus, and then we have the sum of the two terms, or the multiplication of the two terms, which is x1, 1 plus x3, x1, x2. And this we can write as x1 plus x1, x3 plus x1, x2 plus x1, x2 plus x1, x2, x3. And since we have characteristic 2, these two terms will cancel out. So we have finally x1 plus x1 x3 plus x1 x2 x3. So that was one way of deriving the RMF. The second way that we discussed was to use De Morgan's law. So we write x1 x3 prime x1 x2, and what we do here is that we prime this twice, because if we send it into two NOT gates, it will obviously be back to the original expression. And now we can use De Morgan's law for the inner prime, the one that we have here, and write this as x1 x3 prime and x1 x2 prime, and then we have the outer prime still. And now we want to use the fact that a prime can be written as 1 plus a. So this will be equal 1 plus x1 1 plus x3, and then times 1 plus x1 x2. And then let us write this as 1 plus x1 plus x1 x3, 1 plus x1 x2. And then we use the distributive law to write this as 1 plus x1 x2 plus x1 plus x1 x2 plus x1 x3 plus x1 x2 x3. So the ones will cancel out, x1 x2 will cancel out, so what we have left here is x1 plus x1 x3 plus x1 x2 x3. So this is also written on the Reed-Muller canonical form. The last approach that we're going to see an example of is to use the DNF. So this function can be written on the DNF form as x1 x2 x3 prime or x1 x2 prime x3 prime or x1 x2 x3. And here from this one we also have x1 x2 x3 prime, but we have that one already here. So now we have the disjunctive normal form, so what we're going to use is the fact that a prime equals 1 plus a. So this can be written as x1 x2 and 1 plus x3. And then since we have min terms, we can just replace or with a plus. So now we have x1, 1 plus x2, 1 plus x3, and then the last or we can also just exchange with a plus sign because we have min terms, and here we will have x1, x2, x3. So let us just expand this by using the distributive law. So we have x1, x2 plus x1, x2, x3 plus x1 plus x1, x3 plus x1, x2 plus x1, x2, x3 plus again the last term x1, x2, x3. So using characteristic 2, these two will cancel out, and we also have x1, x2 here and here, so they will cancel out. And finally in the end we have x1 plus x1, x3 plus x1, x2, x3 again. So this was our third way of writing the function in the Reed-Muller canonical form. So we have now seen three different ways to do basically the same thing, that is to write it in the Reed-Muller canonical form. Which one is easiest can depend on the situation and what function you have to start with, so try to learn all the ways and then use the one that is best for the given situation.